All right, so here's my data set. Copy this down so you have this maybe in your notes, because you're gonna probably go back. I'm just borrowing a data set from the textbook. I got the one.
Copy on the table.
Yeah. That's it, 95. Okay. If you're curious what this actually is, this is actual data. This is the average price in thousands of dollars of a house in the northeastern United States from 1987 to 1995. And given our extremely outdated textbooks at the time this was published, that was probably just hot off the presses, but now it's kind of old news. So we want to analyze this, okay? First of all, what immediately seems pretty dorky about this table?
It fluctuates.
It fluctuates a lot, sure, that's true. But something else about this seems a little bit crazy. Maybe we want to make a change. So the input variables, values of x, are years. Are those convenient values probably for us to use? No, we could, but it's just going to make why? Why don't we just say, say we're starting in 1987, and these are going to be the number of years since 1987 or something, right? Make sense? So let's do that right now, right? Does that make sense? Those really, that's kind of a dumb way to write all of that. It really doesn't, you don't need to do it that way. We don't need to have we're smart enough that if we get an answer of, like if we want to put in the year 2000, well, we'll just put in, what we put in, 13, right? Instead of having to create a function that's going to deal with those big values of x. Does that make sense? Okay, so instead, let's go years since 1987, and that's going to be our x value, and it's just going to become 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, right? No.
9.
Okay, well, that's 0 though, so it'd be,
It's 8.
so it's 8. Kind of dumb to rewrite this, but I'll do it real quick. Okay? Make sense? Okay. And I'm going to give myself a little more room, and I'm going to put this on the next page. see that okay? All right. So what do we do? Talk to me about how we use these fancy calculators to represent. Let's do a couple things with this. First of all, let's create a scatter plot. Okay, we want to create a scatter plot so we can visually represent the data in a way. That's our, so we kind of see, okay, is there any rhyme or reason to this? So how do we go about
Wait,
getting
where are
it?
you?
Well, here, I don't need to be any place. I'm just going to quit and clear. So we're just starting from the home screen. So where do I go to input that data?
Right.
No,
Second table.
no,
Table
Nah.
stat.
no, no.
Start.
I go
stat,
to
stat plot.
stat.
Oh.
Okay. This is, and that makes sense because what we're going to do is a statistical regression, right? So we're going to go to stats. Within the stats screen, I get three menus. I get the edit menu, which is where we're actually going to start. That allows us to input the data and then to do some other spreadsheet-like stuff with it, storing. And I've never actually done any of that stuff, but clear list I've done. But edit's mostly what we'll use. If we scoot to the right, we get the calculate menu. That's the powerful one for us because that's where all our regressional models are stored. And then the tests, I never even went there, but those are statistical tests that we won't deal with for now. Tests of validity and things like that. But that's really not for us right now. So we're going to go back to edit menu and choose edit. And it takes us to what looks like a spreadsheet. Okay? The L's across the top, the L stands for list. So we're going to make lists of numbers. We always want to set it up so that and if we're consistent, it makes it much easier to work with. We always want to set up our independent variable to be L1 and our dependent variable to be L2 because that's the default for the whole calculator. And then we don't have to go in and make changes to the way the calculator wants to work. Okay, so this is X and that's Y. I've already got stuff in there, so I just want to show you. Is this kind of ringing a bell? People who had me here a couple years ago? Okay. So a couple things you want to be able to do here to manipulate this that's going to help you out. One thing is you want to be able to clear these lists because sometimes you'll have a bunch of numbers in there. You don't need that many. You can clear them individually, but if you go to the heading of the list, you can go clear. Don't hit delete. If you hit delete, you lose the whole column, and I can show you how to get it back. In fact, I'll do one on purpose and then get it back. Hit clear, enter, and it clears the whole column. Okay? If I accidentally do hit delete, which don't do, if I hit delete, it's gone. Then what happens?
Freak out.
You got a bite of calculator. No, you don't. You just go to edit, I think. You go stat, and then set up editor. Okay, number 5. You just hit a 5. And then hit enter, and it resets it. So when I go back to stat, edit, there it is. There's my L2. I'm gonna find the calculator. All right. So let's go up and clear L2. Clear, enter. Okay. And now we're free to put in our data. The easiest way to do this is you can hit enter in between, and enter drops you down vertically down the list. So you can just go, like 0, enter, 1, enter, etc. Okay? Scoot over to the right, it pops you up to the top. Put in all those values.
Do you put them in like that or in thousands?
Whoops. Put them in.
It's because it's in thousands of dollars.
Oh no, we'll just leave it like, if you could either way, we'll leave it like this, and then we'll just know that our answer is going to be in thousands. Yeah. One quick check I always do is I make sure I have the same numbers of entries in each list. And if I don't, I know I screwed up. If I do, it still doesn't mean I didn't, but at least maybe I did it right. Okay? So now what? if I just hit graph, it's not, whoops, okay, hang on, something else I forgot to do. It's been a year. We gotta go up to the y equals editor, and we wanna clear out any functions that are there. And I wanna go up and turn on plot one. Now, let's just double check once to make sure everybody's calculators are set up. I'm sure they are. The default is for a stat plot, but if we go second stat plot, then it gives us the settings for all of our 5 available stat plots. What do these mean? This little icon right here means scatter plot. If I scoot over, I have a choice. If I hit enter for one, I can go in and edit stat plot 1 to be something else. I've got stat plots, I've got line plots, I've got bar graphs, I've got box and whisker plots of 2 kinds with outliers and without. I've got all kinds of things, right? The one, and we'll use this year, we will use 99.99% of the time that one, but we might use box and whisker plot too. That's something that's a possibility. We might do that at some point. But this is one we'll use a lot. So it's on, is the X list L1? Yeah, that's the default, right? The X's I said going L1, Y's going L2. The mark that you want, it might seem like you want to use that little dot, but don't. It's too hard to see. Use the box. The box is easier to see. And I don't know, if you have a color calculator, you can choose, but don't worry about that, obviously. Okay, so we want it on, so we hit enter. The other way you can do this, now we can just quit, it's taken care of. The other way you can do that, once they're set for scatter plots, which they probably all are, is you can just go directly to the y equals editor, and notice now that plot 1 is highlighted. What does that mean? It's on, yeah, it's on. If I go up and unhighlight it, now it's off, and it won't graph, okay? Well, let's turn it on. And let's try graphing. And nothing shows up. How come? I'm not in nearly the right spot, am I? This is just where it happened to be last time I graphed something. Stat plots are typically going to be weird. I mean, the numbers were really big in this case, right? Some of them were at least. So to get it to fit the data that you've entered, there's a really good shortcut. You just go to the zoom menu and you choose zoom stat. So you just always just go zoom 9 and look what it does. How about that? Okay. There's our scatter plot. Okay. So what's it look like?
Little snake.
Kind of. I mean, what basic shape does that seem to have? It looks pretty linear, doesn't it? Right? It looks pretty linear. Maybe it'll end up being linear. Maybe there will be some subtle differences that we can't really eyeball there that might lead it towards a different model. We'll see. Okay, so now that we've got this, we want to try some different regressional models. Okay, this is the cool part. So we're going to go back to stat, calculate, and let's start off with a linear. Oh, before we do any of this though, I'm amazed that I remembered this. Go to mode and make sure that when you look at your settings on mode, you want to make sure that stat diagnostics are set to on.
Yeah, mine.
You'll see that's going to give us, in addition to the regression equation, it's going to give us the correlate. It's going to give us the coefficient of determination.
Does it matter if our calculators in radian or degrees?
Makes no difference.
Do we need to turn off the stat diagnostics after we're done?
No, I just leave it on. Yeah, it won't affect anything else. Yeah. Okay, everybody got that?
Yeah.
Make sure that's on. Okay, and then we're going to go back to stat, calculate menu, and we're going to go down to number 4, linear regression. Okay, so it's already set up to go. The X list is L1, the Y list is L2, frequency list, I'm not even sure what the heck that is. Maybe it's important, but I don't know. Okay, this is important though. Store regression equation. We want to be able to superimpose these regression equations and compare and contrast a little bit. So we want to store that as a variable. We want to store it as a Y variable, so it'll show up in the Y editor. So to do that, we go, I think there was a shortcut to this. I'm sure there was. It was an alpha F4. Oh, that was it. How about that? So we can just go alpha F4 and we'll choose Y1. Okay? And then we're going to go down and hit calculate and look what it does. freaks out a little bit, and then it tells us the equation of the best fit line using a least squares regressional analysis, which is the best kind to use in almost every case. It gives us the equation of that best fit line. Have you ever in the past endured the exercise of like plotting stuff by hand and putting a ruler on? There's no point to ever do that. That's not something that you will ever do again. There's no value to that anymore because you can always do this. No matter what line you draw, it's always going to be inferior to a regressional line. Everybody got exactly the same answer, am I right? Because there's only one exact answer that regressional analysis gives us, so it's uniform, right? Very valuable. So here's the form of the line, y equals ax plus b. So a is like the slope in this case, right? The slope is 3.94, blah, 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 blah. B is the y-intercept, 144 point, blah, 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 right? It's all there. R squared, this is important. There's two things there. R is called the correlation coefficient, and R squared is called I believe, the coefficient of determination. This is the one that we want. R squared can kind of be thought of like the percentage adherence of the data to the actual the line that we drew, the best fit line, okay, or the line to the data.
Like how accurate it is?
Kind of. So you can sort of think of this as being 84.3% accurate.
Is that like the confidence rate?
It's related to confidence, but it's a little bit I think the way it's actually defined as, I think it's defined as 1 minus the variation in y explained by the variation in x. So it's a complicated thing, but you can really sort of interpret it just and this is the way they describe it. Statisticians call it the goodness of fit. It's really a measure of the goodness of fit. Doesn't sound grammatically correct, but that's what they call it. So about 84.3%, okay? So we see what that looks like. I stored this as y1, didn't I? So when I hit graph, there it is. There's our regression line.
Yeah,
Where does it go? How would you describe its path?
Up.
Up? Okay, it's through the middle of the distribution, right? But I could draw a line through the middle of the distribution that looked like this, right? I mean, this is technically through the middle of the distribution, but that's not a very good line, right? It's through the middle of the distribution in such a way that any small sample of points that I take, also the line goes through the middle of the distribution, right? So roughly half are above and half are below, and as you move along the line, taking small samples, it always looks pretty good, right? Make sense?
Yep.
Okay. Okay, so now that's the best fit line. Let's try the next polynomial up, because a line is really just a first degree polynomial, right? Let's try a second degree polynomial, aka quadratic, or what do we call that shape? Parabola. Let's find the best fit parabola, okay? So we'll go. I gotta put this always on top. That's what I have to do. There we go. Okay, so let's go back now to, we've already got the data in, so now we just get to have fun. We can go back to calc, go down to quadratic regression, enter. Oh, I think I got, this thing is slow.
What is your result?
Struggling. 5. I'll just hit a 5. I can do that. Okay, so let's store this one as y2.
Oh.
So alpha F4 2. Calculate. Okay, now, what did we notice? What did we notice here?
There's
It
no
doesn't,
R.
by the way, it doesn't give us a correlation coefficient because that's really just the slope of the line, and there's no slope to this. But it does give us a coefficient of determination, right? So it gives us R squared. So this one's a little better, 84.5% accurate, let's say, okay? Let's go to the graph. There's our line. And there's our parabola.
Wait, so what does it look like if does it go like this?
Well, that's it right there. See, you can hardly even tell that it's curving, but it does a little bit. See what it does? Okay, right?
It eventually starts going down.
Yeah, right. Eventually it's going to turn down, isn't it?
Is that accurate with, like, that could eventually happen with the market?
Right. So hold that thought. That's exactly one of the things we got to think
I
about.
didn't hear
is
what
how-
she said.
She's asking about, does that mean the housing market's eventually gonna crash right there? Right, is that what you're asking? Okay, hold that thought. I want you to answer that question for yourselves here in just a second. So let's go up and let's try a cubic also. Last one, how about? So we go stat, calc, cubic is 6, store it as y3.
How do you get rid of all this? Like, what if I just want to do a normal one? Do I have to
You just
go
clear
through
them
like
out. They show up. When we're done with this, we'll go up and look at y equals, and they'll be in there.
Okay.
So now look at the r squared on that one. Jumped up quite a bit, didn't it? We had like, what, 83 point something, and then 84.5 or something, right? And then it jumped up to 92. So the math gods like this one quite a bit better than the other two. That's a
What does
pretty
this
big
one
jump.
look like?
Well, a cubic, in general, a cubic looks like, it doesn't have to turn twice, but it can turn, it can have as many turning points as the order of the polynomial minus 1, right? So it's a third degree polynomial, so it could look
An N?
like this. I can't draw on that part. It could look like
Oh,
that.
so it's like
Right.
sine.
No, it's just gonna go up, it's gonna go like that, right? Or it might not do that, it might just have an inflection point in the middle and keep going up, right? But it could have up to 2 turning points. A quadratic can have only 1 turning point, and a line can have 0, right? All right, so let's look at the graph. There's our line, pretty good. There's our parabola, only very slightly better. And here's our cubic, which was quite a bit better.
So it looks like the 2 years in the middle are like outliers.
Yeah, there's some, right, and some of them are going to be, and that's the beauty of regressional analysis, is that it's going to compensate for errors in both directions, okay? All right, so talk to me about this then. What are some, and we could keep going with this, but here's something I want to caution you about. Let's do one more, just so I can make this point. Stat, calc, what's the next one up?
Core.
Quartic. And that's as far as high as this one will go, and rarely would we ever go above that anyway. So 7 would be quartic, store it quickly as y4. Okay, and it doesn't change much at all, does it?
It went
Okay.
up by 0.0001.
Okay, and that's not good enough. That's not good enough. If we look at the graph,
Does it look Is it like an N?
quartic can turn, yeah, it could be an M or a W if it turns all the times that it can. It can have 3 turning points. It doesn't have to be symmetric like that either. It could go, it could do something weird too.
Wait,
So
where'd it go?
where is the last? Oh, there it comes. It pretty closely matches that cubic, doesn't it?
Like exactly.
I mean, you can't even see a difference at this scale. Okay. All right. So now let's talk about this, because this is really interesting. And this is, you guys are finally getting to do stuff that really is real. I mean, this is stuff that's important. What could be the potential pros and cons of each of those models? What about the line? Are there any, I mean, you might say just con because it wasn't as good, but are there maybe some pros to that?
It shows you like a period of time if I'm just going up.
It does, and they all do that.
But it's more clear because some scatter plots might be like, it looks like it's
okay, the line is much more conservative. It's not changing very much, which often is a good thing. If you start to adopt regressional models that were the polynomial regressional models with too high of an order of polynomial, then you run into the problem with the function being frenetic. It just goes all over the place. And you don't want that. You want to find a model that is predictive but not complicated, right? You don't want it to be all over the place. If we picked how many points did we have? 9 points. So if we picked a polynomial of the eighth order polynomial, it would have been 100% accurate because it would have gone through all of those points. But it also would have probably done this. It would have probably gone all over the place to get there. That's no good, right? We don't want that. That's not predictive because that would seem to imply that if we were to pick a point, if we wanted to estimate what the housing cost would have been halfway between this year, halfway through the year, it might have said that it was 220, which obviously was probably not accurate, right? We want it to be predictive. Okay, so the line has the advantage of being simple and stable. It didn't quite have as high a quality though, right? The quadratic we would certainly abandon because it is more unstable than the line and didn't get any better, so we can just abandon that one, right? Let's turn that one off. That was the second one, right?
Yeah.
And notice, Delaney, if I go to, there they are, right? So I can just delete them or turn them off. Do you know how to turn one off?
Equal sign.
Yep, go to the equal sign and hit enter, so it turns it off. And really, we could get rid of the quartic too, because wasn't the quartic only very slightly better than the cubic? And we always, if they're equal, or nearly equal, we always want to choose the smaller degree, right? Does it make sense? I'm going to leave it on for just a second though, so I can illustrate a point. Actually, I'm going to leave them all on for just a second. Okay, here's what I want to do. What do we call it when we're trying to estimate a value at an internal point? So if we ask the question, okay, we don't have a record for this, but we need to know an approximation for what the average housing cost would have been in March of, what is this, 87, 89, of March of 1990. Okay, that's not one of our data points, is it? Okay, what do we call that for making an internal estimation? So we're trying to estimate someplace within our data set.
We go to the.
We call that, I'm going to get rid of, let me do this. We call that interpolation. Okay? All of these are pretty good at interpolating because they all stayed fairly consistent, right? Probably the cubic may even be the best at interpolating there because it seemed to follow that trend pretty well, right?
Yeah.
What do we call though, okay, while we're on that subject, what do you think the best estimate of no, never mind. I'll come back to that later. I don't want to confuse you. Okay, so now what's it called if we want to say, okay, based on this model, it ended in 1990, when was it? 1995. Let's estimate what the costs are going to be in 2005. So we're going to make an estimation outside of the data set. What do we call that? Kind of. What do you think the word is? Instead of interpolation, meaning inside, it's going to be extrapolation. Yeah. So if we go outside, a lot of times that's pretty important to be able to do. People are going to collect statistics, collect data, and do an analysis so they can make an estimation about now what's going to happen. Stock market, housing, anything like that, right? You want to know what's our prediction in the future. Well, let's extend this screen out a little bit and see what happens. So let's go, how about if we set the window to go, instead of to 8.8, we need it to go out to like what, 18.8?
Yeah.
10 extra years? Okay, and now we're gonna go, now I think we have to go zoom, oh, now what do we do?
You just grab.
Well, we can, that's not, okay, we can try it, but does anybody know if there's a way to make this thing work with,
Would you not just do zoom static?
we could try it, let's try that. What if we go zoom stat, zoom 9? Oh no, that's gonna change, we can't do that. That's gonna change the window. Let's try zoom, try zoom fit, zoom 0. You gonna do that, or?
Yeah.
Oh, mine's thinking too. Okay, it did it. There's the line. There's the quadratic.
Wait, now I lost, like, now we're gonna count that.
Okay, but here, why is it so big? Watch this. There's the cubic. And here's the quartic. Okay, so this is 10 years ago, right? Let's see what each of these models estimated. Let's go to trace, and then our line, now we're doing plot L1. Plot 1, right, or plot 1. For plot 1, if we do trace, oh, we don't want that one though. We have the up and down arrow to go to the different functions. So we're gonna go down until we get to that one, right? That's Y1, that's the line. So trace 18, right? And that would be the year 2005. Okay, so the line says that the average price of a home in the Northeast would have been about $216,000 10 years ago. Okay, I don't know. That seems somewhat reasonable to me. It's probably a little bit low. Let's go down to, well, it looks like the quadratic's going to be a little bit lower. It's going to be too low. The quadratic's not going to be good. Let's go up to the cubic and see what it says. So we go trace, go down, there's the quadratic, there's the cubic, okay? So we'll go 18, and we get an answer of 821,000 for the average price of a home in the Northeast. That seems a little high, doesn't it?
Yes.
For the average price of a home? Seems a little high. 10 years ago?
A big difference.
That's a big difference. The quartic, if we go to the next one, and we go trace 18. Do you even see what I did there? I don't even know.
Trace, probably click trace before you.
Oh, there we go. Okay, so trace.
Yeah, mine.
Oh, I see. I already hit trace.
Yeah.
I got you. Trace 18. There we go. Enter. Okay, almost $1 million. I don't think that's right. There aren't, not the average house 10 years ago in the whole northeastern part of the United States was not almost $1 million. So what's the moral of the story? Yeah, you got to be careful. That bigger isn't always better when it comes to regression. Just because we got better R-squares for those bigger models does not mean that they were great models in all situations. If we're going to interpolate, sure, maybe that cubic model was pretty good. But when we start extrapolating out there a few years, it's not very good. It's too crazy, right? It changes too quickly. The line was probably the best measure there, wasn't it? Okay? Make sense?
Yeah.
Okay, so I'm going to give you an assignment to do. I don't even know, I'm going to give it to you over the weekend. I'm not even sure how to do this completely. I did a whole bunch of programming last night, and I built regressional engines on Moodle, so they'll do this stuff. But I think I'll give you some questions where you just have to find some kind of direct, where there's definite, explicit, right and wrong answers, where I want you to be able to go in and just do regression. Show me how to do
I forgot
regression.
how to do this on my
On your laptop?
Oh, I mean my calculator.
Calculator. Okay, and I'll put this video. I'll put a link to my, for sure, I'll put a link on all of my course rooms So you can go to the videos.
Is that on Moodle?
On Moodle, yep, on Moodle. But I'm also gonna put one on there, which I think I'm gonna leave open-ended, and it won't even self-grade, it'll be one I'll have to look at. And I gotta think about this a little bit, where I want you to, I'm gonna give you a data set, and I want you to I'm not gonna give you, maybe I'll give you one of these. I want you to really think about it, and I want you to explore what is the best model for maybe one or two of these, and explain kind of why that is the case. And maybe we'll even, I don't know, maybe we'll even get in groups, and I'll have you guys kind of get in groups, and you can maybe even just do one per group or something. But I want you to get a little